Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello again, and thank you for making the intelligent choice to watch IT Pro TV, helping you learn wherever you go. I'm your host, Zach Memphis, as we continue on with 8+ 901, install and configure storage devices. This is part 2. We had part 1. And now we're going to pick it up right in here with probably magnetic hard disk drives. And Wes, Brian is the man bringing you all the information you need to know.
Hey, Zach, thanks for having me back. That is right. We've got a lot of different storage mediums to talk about. Like Zach said in the first episode, we talked a lot about the optical drives. Remember, we have 3 primary storage types that really are something that you're going to need to know, not only in the real world, but also to pass that A+ exam. Remember, we talked about optical drives in the first one. We have a laser that is writing to removable media. It's a mechanical drive, right? We mentioned magnetic media, and again, that's a mechanical type drive that uses some kind of magnetic, electromagnetic energy to store and read information, and then we also have electronic storage. So what we're going to dive into first, like Zach said, is the magnetic media. So let's go ahead and let's dive right in there.
Yay.
Now, when we talk about magnetic media, there are different types of magnetic media. There are what originally we had, or very early on when it came to removable media, which is actually the predecessor, if you will, to the optical discs, were what were known as floppy disks. In the earlier days, these floppy disks could be up to 8 inches long. Pretty much looks like you could roof a house with them, right? They were very, very big. Looks like a shingle out there on your roof. As time progressed, everything's getting smaller and smaller. You probably have maybe seen that over the years. If you look at pictures out there on the internet of old computers and stuff, everything seems to get smaller. Then we would have the 5 1/4 inch floppy disks, and then finally, before they pretty much CD marked pretty much the death blow for the floppies, we had the 3 1/2 inch, right? That's a magnetic type media. Now, what we have for internal storage, and this is not, it's internal and external. External meaning that you can plug it into an external port on or connection on the outside of the system case. Internal meaning it's plugged directly into the motherboard, is what are known as hard disk drives. Now, in this episode, I want you to understand that what we're going to do is we're just really kind of letting you know what the technology is, more in theory type. We do have another episode where we're going to talk about the specifics of the different technologies for hard disk drives. We just kind of want you to understand what kind of storage mediums we have, what kind of storage devices, and then we'll get a little bit more specific in a later episode on those actual connections. So what is a hard disk drive, right? Magnetic media, if you will. I've got a little picture here, and one of the things that you can see is that these hard disk drives, right, little boxes that you see inside of your computer, they're actually made up of a series of platters, right? A lot like a record player was. If you look at the record players, right, and it has this little actuator arm, and this actuator arm floats back and forth, right? The actuator arm is actually what's responsible for using electromagnetic energy to basically put a charge, if you will, magnetic charge on different locations and points across these what are known as platters, right? And these platters do spin just like a record player, and they either are putting a charge onto that platter or they're just reading the charge that's there, right? That's how it distinguishes our binary information, our binary bits, if you will, ones and zeros. Now, one of the things I want you to keep in mind is this actuator arm that you see is a lot like a record player needle. There's a slight difference in the fact that it sits off of these platters. It's in the microns, and micron is 1/1,000,000th of a meter. And when we say a micron, we're talking about so close to those platters, essentially, that even something as thin as an ash fitting in between there could actually scratch the platters themselves. And what happens is as the platters spin, this actuator motor actually moves back and forth, and it's reading different points across the platter or writing information with a charge on different points across these platters to either, again, write or read your data. And they're actually kind of impressive, right? I heard an analogy one time to your hard disk drives, and it went something like this. It said, if we had a technology that we can compare this to on how specific and how precise a magnetic hard drive is, a hard disk drive, it would be like flying a 747 a foot off the ground from Florida here all the way to California and counting every single blade of grass that it crossed paths with from that entire trip, being able to count every single blade of grass, right? It's a very impressive technology. Again, it's on a micro scale, if you will, versus the 747 macro scale, if you will.
Oh, sure.
But very, very important. Now, the only thing that they really call out here in the objectives, right, is the fact that magnetic disks turn at a certain speed. Like I said, if you guys, those of you guys that are maybe, and gals out there that are looking for maybe the specifics on the connection types that these hard disk drives use, we are going to go into what's known as the PC connection episode, and we'll really look at the technologies like serial ATA, SATA drives, if you will. And we'll talk briefly about the old predecessor there, parallel ATA drives and stuff. Those are the connections that these magnetic disks use, and we'll get definitely more specific on that. What I want you to know is that these disks, as they spin faster, it gives you a better performance, right? The faster the disk, the more information that can be written to the drive, again, placed on the drive through electromagnetic charge, or can be written, read off of the drive, right? When it's read off, it's read and sent across the motherboard into memory, and then the CPU can use it. When the CPU is done computing the results of that information, it comes out of memory, comes back around the motherboard, and gets stored through that magnetic charge on the disk that if we pulled the power, well, we could turn around and we could use that information in the future. Now, I do want to make mention, okay, of this, because it doesn't matter what storage device you're using, especially with hard disk drives. If you do pull the power right in the middle of a write operation, then what you potentially get is corrupted information, right? Because it's very, very precise, and it is moving very, very fast. Like you can almost see the points on how fast it's moving, and then it blurs. So you do run the risk of that if you pull the power. I said you can use the information later. If it's in the middle of a write operation, you might corrupt the information. So or the data that's being placed on it. So don't let me mislead you in the fact that just because you pull the power on the system unit, that you could actually get to that data. You could corrupt the information. So we really don't want to do that. Anytime you shut a computer down, you want to perform what's known as a graceful shutdown, right? A graceful shutdown means the operating system closes itself down, and then the hardware sequentially turns itself off so that you don't get data corruption.
I do have a question.
Yes.
So it's in RPMs.
Right, that's right. Revolutions per minute.
So is there a way to calibrate the actual memory, the amount of memory, or no?
No. This is, you know, and really doesn't have to too much to do with the memory per se, because the memory is something that is, you know, our temporary workbench. And really, when it comes to the RPMs and even the drives, there, Zach, you can't really do anything. You know, I think of the cordless drill, and I mean, that might be what you're thinking of. The cordless drill, it's got a variable speed, right? The more we push it, the faster it goes. We don't really set these, right? The manufacturer sets them in. It's a specification. And I'm glad you asked that, because you have to check the specification on the hard drive itself, and it'll tell you. It'll tell you what the RPMs are. And there are really 3 RPMs that they call out here, and I want to go ahead and talk about them each individually. You have 5,400 RPMs, revolutions per minute. I want you to think of those platters, right? Those platters that are running, or that are spinning, right? 5,400 RPMs means 5,400 rotations per minute. You also have 7,200 RPM as well, and 7,200 RPM, again, faster that platter spins, the faster we can get to information, the faster we can read, write information, if you will. Then they also have 10,000 RPMs. All right, now when we talk about 10,000 RPMs, we have to be careful with these drives, because these drives are, for a mechanical drive, are ultra fast. However, because they spin so fast, you have 2 things you have to keep in mind on any system that you're going to use these in. Temperature and noise. All right, temperature, because the faster it's spinning, the hotter the device might get. In fact, we had some of these older, we don't have them right now because we've kind of gone to solid state, which we'll talk about soon. I worked for a company that did have these, they were called 10,000 RPM Velociraptor drives, and they were smoking. I mean, they would move. They also have other ones out there that are on the market too, like 1,500 RPMs. But as of the objectives that we have today, you don't have to worry about 1,500 RPMs. 10,000 RPM drives are very, very expensive. They're again, sometimes more expensive than you can justify the cost. The other thing I mentioned too is with the increased RPMs, you get noise, right? Now you might be thinking, well, what's the problem with noise? Well, I want you to think about a laptop, all right? If you have a laptop, you certainly, one of the things that they don't want to happen is they don't want to have to increase the power that it takes to move, to power the components, because what does that do in your laptop? It shortens your battery life, right? When it comes to laptop computing, there's two major contributing factors, right? Proper thermal management, right? We don't want overheating, which a 10,000 RPM drive is going to increase the heating. You would have to increase the cooling system. The other thing that they're, a laptop's really concerned with is, they want to make them silent. Right, you don't want to be that person that turns your laptop. In fact, Zach and I have laptops on right now, and even if I was to bend this microphone down to the laptop, at best you might be able to hear the fan, but you're not going to hear more than that. And that's because of the fact that laptops are meant to be silent. The other thing that you might see too is that you might have some kind of system that you're using or building for voice recognition, and if you've got a very, very loud machine, it might interfere with things like voice recognition technology that's on it. Now, in enterprise, right? For instance, back here at IT Pro TV, we have a server closet over there. We don't really care about the noise. Servers are loud, very loud. In fact, so loud that if you get into a bank of like 1,000 servers, they're deafening. But that's okay, again, because they're behind an isolated data center, behind an isolated room, security, if you will, and we don't care about that as far as it comes to the noise. So you can see them, you can buy them, 10,000 RPM drives. But a lot of times you're going to see those higher RPM drives are going to be in things like your server environments because, for instance, for example, the cost and just the sheer noise that's behind them.
What's a hot swappable drive? Can we get that?
That is another great concept too, and it's actually a very convenient concept. And hot swappable, when we talk about hot swappable, all right, you have cold swapping, you have warm swapping, and you have hot swapping, okay? And really what they're just called out here is hot swapping, but let's go ahead and talk about the three different types, all right? If I need to replace a video card in a system unit, that is a cold swappable device. And what do I mean by that? I can't, while the machine is under power, open the system unit. You shouldn't do that anyways because you have electrical, the electrical hazard that is. I can't open that case and remove that video card while the machine is turned on, right? So that is a cold swappable device. However, if I have a serial ATA drive, right, and again, we'll get into our PC connections and talk more about those hard drive types, and I have multiple hard drives that are aggregated together in a single system, and I find that that hard drive has failed. Well, I can reach in there and I can pull that hard drive out while the system is still under power and replace it with another one. And I never had to turn the computer off, right? That's cold swap. They also have warm swap. That's like, for instance, when your system's in a low powered state, but that one right there we don't have to worry about as well. Know that hot swapping is the ability to replace any device while the system unit is still maintaining power. Now, you can find this in your home-based desktops, right? A lot of times you'll see this in multi-disk systems that are using the redundant array of independent disk, RAID, which we'll talk about coming up here in a bit. And you can definitely find this inside of things like your enterprise environments, because when you have these computers, if you will, servers, computers, if you will, that have multiple disks, I mean 15, 20, 100 different hard drives, and a technician comes in and they see a blinking red light on the face of one of those drives, signaling a drive failure, they don't want to have to turn the whole entire system off, right? Because time is money, and anytime you don't have data access to your data, your company runs the risk of losing information. So what they can do is they can remove that hard drive while the system's still powered on, right? And then they can put the new drive in place. Here's one that's another component that is hot swappable, and you probably use it on a daily basis, or maybe you do, right? You ever had a little thumb drive? You plug it into your machine. Did you have to turn off your machine to plug it in or unplug it? And the answer is no, right? USB. Your USB-based device is little thumb drives, right? These are examples of hot swappable devices. I can plug them into the machine is still under power, and at the same time, I have the ability to unplug the device, likewise, through certain safe means without actually powering the whole entire system down. So those are hot swappable.
Solid state flash drives. You had kind of mentioned solid state a little while ago, or
yeah,
no?
definitely.
Yeah.
That is what I mentioned when I said electronic drives, right? We have electronic storage too. And electronic storage is exactly like it sounds. It means we're not using magnetic energy, and we're not using an optical light source, right, to read or write the information. In this point, what we're doing is we're using electricity to store and read that information. And that's essentially what a solid state drive is. They call them SSDs, right? Solid state drive uses technically what's called NAND flash memory, but just think of it as a non-volatile memory, and they're memory chips that are in the device itself using an electronic current, if you will, to store and read that information. In fact, I've got kind of an example here, one of these OCZ solid state drives. And the OCZ solid state drives, and the OCZ is just a brand, guys. Don't think of that as an actual technology, if you will. That's the manufacturer. Corsair, Kingston, a lot of different companies make these. Intel makes solid state drives. But notice that it's using what looks like memory chips, and that's essentially what they are. Those are those non-volatile chips that we've talked about in our memory section, right? That are perfect for storing information because of the fact that we can remove the power, and when we remove the power, we can still get access to the data at a later time, unlike volatile memory, our system memory, if you will, again, that requires the presence of an electrical current. All right, now these are non-mechanical drives, right? You can see the big difference here. Let me see if I go back to the magnetic drive, right? The magnetic drive, we have multiple platters. They're going to be spinning. They've got an actuator arm that reads the information. You have an actuator motor that is responsible with a bearing in it for moving that, like the record player needle, back and forth across the drive. But if you consider or compare that with this drive, notice that all we have are these memory chips. All right, now, in the memory episode that we did, one of the things I told you that differentiates one of the main contributors to why these are slow to take hold, in fact, I say slow to take hold, that might be true 10 years ago, but not so anymore, is the fact that non-volatile memory is very expensive, right? So you'll see that the price point on these is still up there. It's come down considerably. When they first came out, it's about $2 a gig, which is very expensive. If you figure that you had, I don't know, a 100 gig drive, you're talking $200 for the drive versus something that, you know, a mechanical drive that if you spent $200, you would have the biggest drive on the block, again, versus like, I don't know, 50 cents to 80 cents a gig. Today, they're actually come down quite a bit in price. They're actually finding ways to make them more efficient, if you will. And again, the price points come down, but they're still very expensive compared to the mechanical drive. However, one of the benefits they have is, again, going back to the fact that they're non-mechanical, is I don't have to wait for all these components to start up, to initiate, to seek, if you will, and then have that arm find on the mechanical drive, right, find the location of where your data is. All we do is we put an electrical charge, and I don't really know how fast electricity moves because we're not engineers here, and this isn't a physics class, right? Definitely moves faster than I do. Is the fact that we just have to wait for the electrical current to be present, right? So we get very, very fast access times, right? We get very, very fast read times, and there are a couple of different drives out there, and I don't think they call this out on the exam, but I just kind of want to briefly mention it here. They have what are known as single-level cell solid-state drives. You might hear them called SLC, SSDs. They also have what are known as multi-level cell drives, and basically it's just about how much information can be stored on the data and also expense and speed. A single level cell, again, because it's single level, can only store smaller capacities, but the drive controller, if you will, just kind of we talked about a memory controller in our memory episodes that actually controls access to the memory, right? You have this you have this component within all the drives that are called a drive controller, and it's what allows you to access the information. Well, in the single level cell drives, the drive controllers can access the information a lot faster because they don't have to do a lot of guesswork because of the fact that it's just a single level. Multi-level cells allow you to store more information, so the capacities are greater at a smaller price point. However, due to the multiple levels that you can store the information, they can be prone to things like errors, and the speeds are a little bit smaller. However, bigger capacity at a smaller price point makes them one of the most common SSD types that we have. Now, you did mention one other thing that I do want to talk about, and that is flash drives. And flash drives really are using the same concept, all right? In fact, I got a picture of here, one. You've probably seen these a lot. We call them thumb drives, right? USB thumb drives, flash drives, if you will. Flash drives are also using NAND flash memory as well. Just like I showed you the solid state drive here, what you would see I would almost guarantee you, if you pull the shell off of this flash drive, then what you're going to see is probably just a single chip, right? A single one of those non-volatile memory chips that when you plug in, it allows you that electrical, the electrical storage. So that essentially is what the flash drive is. It's a lot like the solid state drive, but it's using a different, well, I don't know, solid state drives can use USB connections as well, but for the most part, your internal SSDs are using your typical hard drive protocols that we talk about in our PC connection.
Awesome. And I suppose those are pricier?
The flash drives, they've come down in price. When they first came out, they're so common now today, again, and that they've come down. They're very cheap. What really gets price point on that one, Zach, is the fact that the bigger the capacity,
right,
the more chips they have to put on there, and it's, you know, again, more chips, more manufacturer cost, and that translates to consumers out there, right, paying more money for them. So you can see like 128 gig thumb drives today, and those are still have a pretty good price point. You can see some that I believe are up to 256 gigs on a little stick like that, but very, very expensive. Like the one that I had up there, that was a 4 gig drive. Those today are almost a dime a dozen.
Oh, yeah.
Now, when they first came out, those were very expensive. Yeah. You get a 4 gig drive, and you're talking about a lot of money for those. But again, just like anything, as time progresses, as the technology gets better, and as capacities that we had today become yesterday's news, those smaller capacities actually cost less money. All right, so one of the next things I want to talk about, and probably I can see Zach saying, we might have to go into a part 3 here. One of the last things I want to talk about in this episode here are compact flash. And compact flash is using the same concept of electrical storage medium. Now, this is also just like the flash drive, the little thumb drive, this is removable media, right? So it's a removable storage media. And there are a few different formats. And I don't know how specific they're going to get on the exam because you just never really know what the questions are that you're going to get. There's large banks, large pools of questions that CompTIA gives you. But let's go ahead and let's talk about some of the nuts and bolts of compact flash and give you some of the specifications. I know, guys, standards they're not fun, but if you can remember them for the exam, you can do great. And then once you pass your exam, you can forget the standards and then just Google them when you need to, use the search engine. But you won't be able to Google inside of the exam booth, and that's why I want to make sure that you're prepared. I got an example of some of these different flash drive types, or compact flash, and you've probably seen them. And if any of you guys, which I know many of you do, I say if any of you guys and gals out there have them, I know you do, I'm sure have probably used these a lot more, especially if you have things like mobile devices, like right?
Micro SD.
That's exactly it. And those are some of the first ones that they call out too. And that, the one that Zach mentioned is actually up here on the right-hand side of your screen. And you can see I went ahead and put the 3 form factors. These are actually an adapter that allows you the inner compatibility, so that if I have one of the smallest ones, I could put that in a bigger sleeve, if you will, and then finally put that in a bigger sleeve. And that's something known as Secure Digital. Secure Digital is the SD card that you mentioned, and you can see it comes in 3 formats, and the formats that you see are these up here. You have what's known as a full-size SD card, and that's exactly what it sounds like. It's a big SD card. Then you have what's known as the mini SD card, and you also have the micro SD card. And those are called form factors. Remember what a form factor is? In this case, it is the size of the component. Unlike a motherboard that also describes things like the characteristics. When we talk about form factor in this context, what we're talking really is the size. And there's 3 different form factors of Secure Digital. Secure Digital, by itself, an SD card, that's a full size, right? Then you have the mini SD, and then you have the micro SD. Now, I do want you to understand that you have a few different capacities, and that's also good to know because you might see I'll give you an example. You might see a micro SDHC. Boy, that's a bunch of alphabet soup, all right? So let me help you out. Micro, Secure Digital, high capacity. So you have 3 capacities. You have what's known as standard capacity, which is kind of becoming a thing of the past. I mean, they're still out there. They're interchangeable, but very small capacities. We're talking megabytes, right? But then you have high capacity, and you also have extended capacity. Some of the extended capacities are up to 128 gigs, and I believe beyond 256 gigs just on a little micro card. So absolutely amazing that you can get all of that information on something that really is that big, right? So definitely keep that in mind. That's the Secure Digital. Some of the other ones that they have what's known as the XD card, right? The XD card is an older standard. It was used in digital cameras, right? It's real limited usage. It didn't have a lot of different manufacturers that were using it, and Secure Digital, the SD cards have pretty much made these go by the wayside, and that's what's more common today. You can see capacities. It's going to, some of you guys might laugh at this one, but it's down to 16 megs all the way up to right around 2 gigs, right? And with Secure Digital, the high capacities that they have and then the extended capacities that they have, XD, the fact of the matter is Secure Digital's pretty much run out on how, how we store information on mobile devices as well. The other one that they have is what is known as the eMMC, all right? That is the Embedded Multimedia Card. And these were, again, typically they had an embedded circuit board, if you will. Again, and it's non-volatile memory, just like all the other cards are, used in mobile phones and tablets. One of the good things about the eMMC card was the fact that it had speeds that were comparable to what our solid-state drives are, which is one of the things that kind of made it very convenient. However, the majority of these cards today that you find outside of an exam environment are really going to be the SD card. So those are a few different types of your cards. I think, Zach, the one last thing I want to take care of is something known as the tape drive. And this is, you know, Zach, you had a great question before you even started the show. You said, are you kidding me? Really? Tape drives? We're going back to the days of the cassette tape?
Everything old is new again.
That's right. You know, it seems like technology's cycling around on itself, right? And to answer your question, yes, that's exactly what it is. It's the reeled, you know, the reeled magnetic tape. And you might be asking yourself, well, what is this, 1980? Right? Even before that, right? The old 8-tracks, right? In the late 70s and stuff. Mm-hmm. And really, the concept is the same. It's another form of magnetic media, and we still use it today. However, one of the things that tape drives are very, very good at is holding large amounts of data. I mean large amounts of data. Sony's got some that are in the works. It's either Sony or IBM, and I can't think of the two giants, which of the giants it is, that can put up to 185 terabytes on a single tape. Okay, so they're perfect for archival, right? We know it as backups. If you ever hear a data archival, don't let that confuse you. We're going to talk more about backups when we get, for instance, into 902, the 902 episodes. But our crucial set of information that we can't afford to lose, we can put it on tapes, right? Now, understand that the information is read sequential, much like the tape, you know, the old tape cassettes would be, right? Mm-hmm. If you remember the tape cassettes, you would have to fast forward, right, to the next track. You couldn't just like the DVDs. I still have tons of them. Oh, yeah, there we go. You're aging yourself. Sorry to do that to you on camera there, but and that's right. They're read sequential, and that's important to understand. Is that you know the data's read sequential. Again, it's a magnetic interface. They are removable media used for backups today, and you can see capacities anywhere, commonly anywhere from 100 gigs all the way up to 12.8 terabytes of information. And what I want you to know for the exam is not some of the formats like they have. The most common format, if you want to go out and look, is the Ultrium 8 standard, and it's called a LTO tape. That's a linear tape open standard. And just for the most part, know that tape drives are there, know that we use them. They're very high speed. Like they have the speed, those spinning wheels can spin just as fast, if not in some cases faster than the internal magnetic drives that we have. The LTO standard, I think, does about 160 megabyte sequential reads, and that's what the very first serial ATA standard support, more. The original serial ATA standard that came out only supported 150 megabyte transfer speed. So very, very fast. Again, they're expensive, but they're typically used inside of enterprises that need to archive their information and they can't afford to lose it.
Well, Wes, because magnetic tape degrades over time, do they take that information then and then store that somewhere else?
That is a great question, and yes, they do, because it is no different than some of the issues you would have back when we had tape cassettes were so common, right? I'm sure you probably did this. I know I did this. You leave, especially here in Florida, you leave it on the dashboard. You come back after a good afternoon of very, very hot weather, and the tape is warped. So yeah, they definitely have to seal these in climate control systems. You have entire robotic machinery too. If you've ever seen some of your like I don't know, like sci-fi movies where you have an arm that comes out, pulls a tape, pulls it down, that's what that machine is doing. That machine is finding tape data and is moving it down. Now that's very, very expensive, but you might be that robot and it might be part of your job as a backup operator, but it's a great question, and you do have to store these in a climate controlled and secure system or a secure location to make sure that you don't lose the information, because like any other magnetic media, you do run the risk of what's known as bit rot or data rot in the fact that the media can start to lose its magnetic charge, and you certainly can't keep them next to like magnets because it can scramble the information. So those are some of the considerations that we have to just know about and consider.
Wes, awesome job. Thank you very much. And this is part 2 of Install and Configure Storage Devices A+901. And you want to catch part 1, and there'll be a part 3. Hey, thank you for watching IT Pro TV, where we help you learn wherever you go. I'm Zach Memis.
And I'm Wes Bryan.
And we'll see you real soon.
Thank you for watching IT Pro TV.